Live from Grand Canyon. Today, let's look at the basics of geologic time. The geologic time scale is a little bit like a calendar. Originally, it was made up by using several important stratigraphic principles that I will detail for you throughout today's lecture. Later, all of the dates applied to it, that is ages millions of years ago and tens of thousands of years ago and billions of years ago, these were applied with data that was collected using absolute or radiometric dating methods. We're not going to worry about any of these specific names, but you might be interested to learn about some of the origins of them. So some of them have Greek or Latin roots, and others are named for people or places around the world. So if you want to explore that, by all means, be my guest. For our purposes, we're going to focus primarily on relative dating, but I will touch a little tiny bit on absolute dating. Both of these methods are used together to determine the age of rocks, fossils, and rock formations. Relative dating is based upon the principle of uniformitarianism, which was proposed by an old white dude named James Hutton back in the 1700s. You could read more about him in this great book called The Man Who Found Time by Jack Repchak. Uniformitarianism is simply the principle that suggests that ongoing processes that we see today are the same as they have been ongoing in the past. That is, the present is the key to the past. So this idea that we can look around and see a river running today and understand that that river likely ran like that in the past, and rivers that no longer exist today did exist in the past, and they also ran the way that the river you're looking at runs. This is the foundation for modern geology. This is something that you might recognize as Occam's razor in other subjects, which is the simplest explanation is the most likely one. So for an example, we can look at this picture of sand dunes. This is the surface of a sand dune. It is sand grains. They are rippled from the wind having blown them. And you might recognize this on beaches or in deserts, and you can see them forming and actively watch those ripples change in real time. And if you were to come across this rock with ripple marks in it made of sand, this is a rock of sandstone, you could say, oh, well, maybe that used to be a sand dune, and it probably did. Do you know if it formed in the desert or on a beach? Right offhand, no, but you could look for other evidence for that, such as footprints or plant fossils or shell fossils. There are 6 relative age principles that I will walk you through, and all of these are built upon the primary principle of uniformitarianism. Superposition, original horizontality, and lateral continuity were all proposed by another old white guy named Nicholas Steno. He was actually born Niels Stenson, but there was this trend back in the 1600s and 1700s to Latinize one's name. You could read more about him in The Seashell on the Mountaintop by Alan Cutler. His 3 principles of stratigraphy, which are the founding principles for all of stratigraphic methods today, is simply the way we look at interpreting and reading the layers of rocks like the pages of a book. Let's start with superposition. The principle of superposition states that the youngest rocks are on the top and the oldest rocks are on the bottom. A layering of sediments occurs in sequence over time and as a result of time and density. So the first heaviest particles will fall out of a fluid, out of water first, land on the bottom, and over time, layers of sediment or layers of lava will build up on top of those older, earlier bottom layers. You can think about this like building a sandwich. If you start with a piece of bread, that'll be your first oldest layer. If you spread mustard on it, that goes on top of the bread. You spread it like this, not holding the bread upside down. Maybe put some cheese on that, some lettuce. All of these stacks go in sequence, and the first stack or the oldest piece is on the bottom, stacking all the way up to the youngest on the top. So the principle of superposition states that the oldest layers are found at the base of a geologic sequence and the youngest layers are above. We can also look at a cake, a geological layer cake, to represent that. Why don't you hit pause and think about all of these sequences and what order you would have assembled this cake in to practice the principle of superposition. Next, the principle of original horizontality. To the left, we have a photograph of some recently formed soil at the edge of a river, and we have actually got very fine seasonal stacks of leaves and sand here because this river cuts through a forest. The principle of original horizontality states that sedimentary layers are originally deposited nearly horizontal and parallel to the Earth's surface. You can see this represented really well in the layers of silt, sand, and leaves in the picture on the left. Lava also follows this law. It is a viscous fluid, and it will flatten out as it flows along the Earth's surface. You can take from the principle of original horizontality that any layer that is not horizontal must have been disrupted after it was deposited. If we look at the Grand Canyon in a photograph that is very similar to my background today, you can see that most of the layers in this point of view are horizontal. And so these layers are in the position that they were when they were originally deposited as sediments before they formed into sedimentary rock. If you look at this photograph, which is in Scotland, this is Hutton's famous outcrop from which he derived his principle of uniformitarianism. These rocks in the foreground are definitely not horizontal. And Hutton noticed that too. In the background, way in the background, you can see that those layers are horizontal. I don't know if you can make those out back there. But these angled ones, something has happened to them since they were deposited. You can see though that they are all parallel to each other. So probably they were deposited horizontally as per the principle of original horizontality. And then they were uplifted and tilted on end by some geologic event. And you don't know what that is because you don't have a time machine. The principle of lateral continuity is really well exhibited in my background and in this photograph from within the Colorado Plateau on the left. And that is that strata or layers extend continuously in all directions. So in the small view of a flash flood in an arroyo, you could say that this layer on this side of the stream is the same layer as this layer on this other side of the stream. That once they were connected, and they were connected before the stream cut through and broke through those layers. The principle of lateral continuity extends far beyond small streams like this. On the Grand Canyon with the wide Colorado River, we see that continuity between rock layers on both sides. And beyond that as well, wherever you can map the rock units, anywhere that it's been cut through or disrupted, suggests still that originally it was one single continuous layer at one point in time. So this is a closer up view without me blocking it of the Grand Canyon and these continuous layers across the Colorado River. It is easier and simpler to explain that these were once one continuous layer that the Colorado River cut through. Then these were two rock formations that formed identically in thickness and composition and density simultaneously, but not connected. The simpler explanation is lateral continuity. If we broaden our view again in Grand Canyon, looking at the Colorado Plateau, you can really follow these distinctly colored layers all the way across this plateau. And if we look at this top whiter buff colored unit, you can follow it all the way around, well into the Colorado Plateau, beyond the Grand Canyon. This is all a principle, this is all the application of the principle of lateral continuity. These principles might seem pretty logical, but when you actually practice using them, sometimes you can get tripped up. And logical and simplicity is really what we build this foundation of geology upon. Here, if we explore canyonlands in Utah, we have even less rock remaining than in the plateau earlier. These single pillars of rocks were once all part of one unit, and there's hardly any of this layer remaining. but we can still say that they are the same rock type, they're the same rock age, and likely they were all once one layer that's been very much eroded all the way through, just leaving these single pillars behind. Next, we'll move on to Lyell's two principles of stratigraphy. Lyell also is one of our old white guys. You can read more about him in The Man Who Found Time, the same book that you can read about Hutton. Lyell provided cogent, measurable, and repeatable methodologies that supported Hutton's concept of uniformitarianism. And these two things that he contributed to our principles of stratigraphy are the principle of cross-cutting relationships and the principle of inclusions. Let's have a look. The principle of cross-cutting relationships states that a rock unit, sediment body, or fault that cuts through another geologic unit must be younger than the unit that was cut. So let's look at the top left image here that I've annotated with some words. You can't really make out the two distinct rock types. The top one is slightly darker than the bottom one, and they look pretty similar. You can see that there is a distinct horizontal line between the two of them. And that is what we call a bedding plane. So this lower sandstone is one sandstone bed, and this upper sandstone is a second sandstone bed. So this line between them is a bedding plane that occurs between those two sandstone beds. I've tried to illustrate that that plane is offset. It's offset by a fault. So the left side of the fault has moved the two beds down relative to the right side of the fault. This fault plane had to cut the rocks that already existed in order to cut them. So that makes the fault younger than the two layers of rocks in the background. So with a fault, it might be pretty straightforward. You can think back to the sandwich analogy. If you were to slice your sandwich in half, that's the equivalent of a fault plane. The sandwich had to exist first in order to be sliced. You can't pre-slice an area, build a sandwich in it, and it will come out sliced. That doesn't work. In the lower image on the left, we have several rock units that are featured. You can see a black, almost straight rock unit, a white, slightly bent rock unit, and then a medium gray kind of mottled looking rock unit. Why don't you hit pause and decide what the order of these are, with 1 being the oldest and 3 being the youngest. Let's see how you did. The first unit is this mottled gray one. That mottled gray one is cut by both the white one and the black one. So it has to be the oldest. The white unit is cut by the black unit, so it must be the second oldest, and the youngest one is the black unit. So the order in this particular photograph is first the gray blob of rock formed, then it was cut through, it was intruded by the white rock, then it was intruded again by the black rock. And that's the principle of cross-cutting relationships. Now, the principle of included fragments works in exactly the opposite way. An included fragment is an item or a rock item, or in this case, I've got a picture of amber with insects in it. It's any included fragment that is discrete and not connected externally to something else. So in the lower photograph, we have one of my favorite included fragments, which is a heart-shaped olivine xenolith. Xenolith is a fun Greek-rooted geologic term for you. And of course, the top we have amber with insects. So the principle of included fragments states that any fragment contained entirely within a larger rock unit must be older than the rock in which it is enclosed. So the bugs were there first, then they were encased in the amber. The olivine xenolith existed first, and then it got included within this basalt. You can think about this like a cookie. A chocolate chip exists first, and then you can include it within cookie dough. Now let's examine one more thing which are unconformities. Unconformities represent a surface in the rock record that either was a period where nothing was deposited, or more likely is a period where erosion removed other material. It is a form of cross-cutting relationship, but it's easier probably for you to keep them separate for now. So for example, if we think back to the stream cutting through those rock layers I showed you a few slides ago, that stream is eroding out material from the rock layers. And then after that stream dries up, if it gets filled in with something else, that surface where the stream was once touching is what we would in the future call an unconformity. So if we look at the photo on the left, you can see there is horizontal, sort of fragmented soil, sand looking material on the top with trees and shrubs growing in it. And below you see bare rock. Not only do you see bare rock, but you can make out distinct layers. And they're gently curving in a sort of broad U shape. So in this case, the unconformity is the boundary between the broad U shape and the overlying younger material. Here we would say pretty confidently, this must be an erosional surface. This broad U shape, remember original horizontality? These layers were probably once horizontal. Then some geologic event caused them to fold gently, and then some erosional event cut the surface off and flattened it out, making it horizontal again and cutting off the rest of these layers. After that erosion was done, more material was laid down, and that's laid down horizontally on top. Here's an example with my friends Dirk and Rob. This is also in Grand Canyon. They've got their hands on what's known as the Great Unconformity. And it's called the Great Unconformity because it represents over 300 million years of missing geologic material. Below, they have their hands on some metamorphic old rocks called the Vishnu schist, and above they have their, well, Dirk has his hand on the above rocks, which are the horizontally deposited sedimentary rocks. So we have metamorphic rocks below, sedimentary rocks above, and you might notice the fabric in these metamorphic rocks below is near vertical. So it is very far from horizontal, whereas the material above is perfectly horizontal. So this is an example of an unconformity as well. Here's a drawing that I made for you where you can practice your skills again. So hit pause and try to figure out the order of units and the events that formed them. And I'll give you a moment to do that. And then you can check and see how you did. So the first thing we should do with this particular illustration, this high quality sketch, is sort it out into packages where we can see the same thing that's taken place on them. So for example, this upper portion, everything is more or less horizontal. This section with the X's in it is kind of at a steep, nearly vertical angle. And this material below is kind of like a broad upside down U shape or a broad A shape. And all of it is parallel. So we could sort this out then into three, what we might call geologic packages. So I'm going to identify them as package 1 on the bottom, package 2 on the top, and package 3 with the X's. Of these three, which is the one that occurred first? That is package 1, the bottom one. So we first have to employ the principle of superposition, which states that the oldest units are at the bottom of the rock sequence. Then we also have to employ the principle of original horizontality, which suggests that originally these layers should have been horizontal. And we also need to use the principle of lateral continuity, which suggests that this dotted layer continues into this dotted layer on the other side. And in fact, all of these layers are continuous on either side of this third package. So with those principles being used, we can unravel this sequence and say that this white unit, this big dotted unit, this white unit, this small dotted unit, this lined unit, and this white unit were all originally deposited horizontally, and then some geological event folded them. And that's package 1. Now, to get from package 1 to package 2, which is horizontal, what we have in between them is an unconformity. And since these lower units show folding, we know that erosion must have happened to even out that surface. Otherwise, we would have a fully arched set of rock units, and we don't. So after erosion planed down the lower units, then these upper 1, 2, 3, 4 layers were deposited horizontally on top. Now we can use the principle of cross-cutting relationships to say that this unit with the X's on it has cut through or intruded all the geologic units, so it must be younger than everything it cuts through. So it's our last geologic layer to come into play. Then, after that, we must have another period of erosion that erodes the top surface. And we know that because there's this sudden cutoff of this intrusion, and that just seems kind of strange. This should have ended in a volcano, but instead there's a sheep grazing on top. So there must have been a long period of erosion happening. And then soil formation and grass growing and farmers coming in and bringing sheep, and et cetera, et cetera. So these principles of stratigraphy or stratigraphic principles go into a field of geology that's known as stratigraphy. What is that? That is the science of correlating rock units. What we do to do that is use their relative age dating techniques that we've just gone through, which is based upon their lithology, which is another term for rock type. Then we use the principle of lateral continuity to assume that units are mappable over a wider area, and use lithology or rock type and relative ages and lateral continuity to piece together the geologic puzzle of landscapes. So it might look a little bit like this. If you map an area or 4 different areas and you look at all of the rock units that make them up, you kind of play a connect the dots game to connect them across wide areas. And from there, we can make geologic maps. So this is a map, again, of Grand Canyon. They're really spectacular maps, and this is because of the action of rivers eroding through, or in this case, one river eroding through and several side drainages that meet it. And everywhere that there are these layers shown on this map is representing a geologic rock type. We can see all of these layers that are stacked vertically, that are layered horizontally. We can see them in the map view because of the Grand Canyon's V shape. And how we visualize that in 3 dimensions can be a bit tricky. There's this great tool that's free online called Visible Geology, and you can erode a sequence of made up rock layers to see how they would look in map view to help you understand that visualization. All right, and then to wrap up, what about absolute dating? Well, you might remember this geologic timescale I showed at the beginning and mentioned all of the numbers on here come from this technique. Well, we'll just take a quick snapshot view at how those numbers are derived. It's all about half-lives and radioactive decay. So there are many isotopes of elements that exist in nature that are naturally unstable. We call them radioisotopes. They are unstable and emit spontaneously alpha particles or beta particles or electrons, and you don't need to worry about this for this class. And upon emitting these particles, they decay radioactively into a new element. So as a result, that becomes a new mineral. So what we're looking at on this graph is a proportion of parent atoms remaining on the y-axis and time units on the x-axis. So a half-life is the amount of time it takes for half of the radioisotopes to decay into a new, more stable isotope. So we start at time 0 with 100% of the radioactive isotopes in their naturally occurring unstable forms. And after one half-life has passed, that is one time unit on this graph, after one half-life, half the radioisotopes have decayed and formed into a new, more stable form. After two half-lives, 50% of the remaining parent radioisotopes have decayed again. So now we have a new ratio of 1/4 original unstable radioisotopes and 3/4 stable new isotopes. And this goes on for multiple half-lives. So what a geologist will do, or a thermochronologist or a geochronologist will do, is they'll start with what the ratio looks like today of a known decay product and a known source product or radioisotope, look at that ratio, and then back calculate how many half-lives have passed. From there, they can calculate an approximate age. And this is pretty complicated stuff, but that is how the principle works. There are several commonly used radioisotopes, and I've listed them here for you. Why don't you take a moment to decide which is the most likely one used in geologic questions. And while you're doing that, I'll tell you that these half-lives that have been calculated, this is what they will use once they've determined, say, 5 half-lives have passed. Then you can use the known time for a half-life to compute an age of how old that particular rock that you're sampled happens to be. And as you look at this page here, you might also see that carbon-14 with a half-life of just over 5,000 years or just under 6,000 years is pretty limiting for using beyond paleontology in recent paleontological applications. And really, it's about only useful for archaeological applications. And that wraps things up. I'll see you next time.